to be talking about different types of patterns, how we can expand on the pattern, basically just an introductory into linear relations. So, what we have first of all for this lesson is on page 154 of your textbook. If you have that available, you might want to flip to it, but I also just illustrated basically what that's talking about. So, this is kind of a lesson where it was nice to be in class because you get to kind of guess and check at a lot of these examples before we talk about it as a class, but I'll just describe everything in the video, so no big deal, okay? Basically what's going on is we've got this banquet hall. We've got tables in there. We need to fill those tables with people around it, and we want to figure out a pattern so that we can kind of proportion in as many people as we can with a specific amount of tables. Okay, so basically what the textbook gives us is that we have one table and we can fit 4 people around that table. When we have 2 tables, we can now fit 6 people around the table. So all of the dots around the table are the people. When we have 3 tables, we can now fit 8 people around the table. Okay? And then the textbook invites us to just try the next 2 sets of tables. Okay, so we went from 1 table to 2 to 3. Now I'm going to draw a pattern if we had 4 tables, and we can see how many people will fit at them. So 1, 2, 3, and 4. So I've got these 2 people on each end of my tables, and then obviously I need lots of people in the middle sections. Okay, so I end up with 4 tables and now 10 people. I can do the next one in the pattern, so I'll go again, draw it over here. This time it'll be 5 tables. 1, 2, 3, 4, and 5. And once again, I'm going to place those 2 people on the ends of the table, or the heads of the table, I guess. And everybody else around the table. 1, 2, 3, 4, and 5. 8, 9, and 10. Okay. Beautiful. So now we have 5 tables here, and 12 people can fit around those 5 tables. Okay? So the textbook asks us to do that. It's pretty easy to follow the pattern. Okay? You can fit how many people are around those tables. And the textbook asks us to figure out what changes and what stays the same when we add those tables. Okay? So I used specific colors for a very specific reason on this. Is something that I noticed on all of these tables is that as we stretch out the number of tables that we're putting in, we still always have 2 people as the head of the table, or on the ends of the table. Okay, so I made them in blue. So here we've got 2, here we've got 2, here 2, here 2, here 2. So they're always consistently on the ends of those tables. That's what I think stays the same. Okay? What changes is obviously the number of tables we're using, the number of people that fit at the table, but also something that I notice consistently changing is when we add in a table, we now get 2 more people. We add another table, we get 2 more people. Add another table, 2 more people, and so on. So we have that continuous pattern. So when I have 1 table, I have 4 people that can sit around it. When I have 2 tables, 6 people sit around it. 3 tables, 8 people. 4 tables, 10 people. 5 tables, 12 people. So we notice this consistent change where it's going up by 2 every time. When you introduce a new table, you introduce 2 new people that can sit around it. So what changes? 2 new people per table, maybe per new table, if I wanted to be more specific. What stays the same? 2 people on each end, or the head of the table. Okay? And then the next thing that we're asked to do is think about future table arrangements. So we could talk about 6 tables, find out how many people sit there, 10 tables, 25 tables, and so on. And there's lots of different strategies that we can use to get those answers. So when I asked the class, how could we figure out how many people are sitting at 6 tables, there were lots of strategies. One strategy was just draw the next picture. We drew 5 tables, just draw the next one. That'll be 6 tables, count the people, you get an answer. Another strategy that other people were using is they just follow the pattern. So they know it's going up by 2 every time. We managed to already get to 5 tables, so then the 6th table will go up by 2 more people, and then it would be 14 people. Beautiful, okay? That's another strategy that we can use. So both of those strategies are really nice and easy strategy when we have low table numbers. But then when we started to get the higher table numbers, like 10 tables, I don't know that I really want to draw a picture with 10 tables. I can, it won't take too long. Okay, so that is an option. I could still follow that pattern, that is totally an option. And figure out how many people would sit at 10 tables. It's just a little bit more annoying. Okay? And then when we start talking about 25 tables, which is a really big number, I don't want to draw 25 tables. I assume you don't want to draw 25 tables. I don't want to follow the pattern all the way up to 25 tables. It just becomes more of a long process. And then thinking about a number like 100 tables, that's way too many for me to want to draw them or for wanting to follow the pattern. So we need another strategy that can work for the larger options as well. So what I had everyone in the class do is try and figure out the relationship between the tables and the people. Gave everyone a few minutes, they guessed, got some answers down, and we ended up finding out that there is a really big relationship. Okay, or not a big relationship, but an important one. So the relationship between the tables and the people can come down to an equation. We know that we have a change, that there's 2 new people per every table. If you remember all the way back to Unit 1, the word per means we multiply. So 2 people multiplied by every table. We don't really know how many tables there are, that's what's always changing for us. Okay, so I'm just going to use a variable and call it t. We also know that there's always going to be those 2 people on the end. So we're always going to have to account for those 2 people and put them into the equation as well. So I'm adding 2 to that. That combination will tell me how many people I have. So that will be equal to the people. So I just turned this relationship into an equation. Okay. That's going to make my life way easier. I can use this strategy, this equation, to figure out how many people are at 6 tables, how many are at 10 tables, and how many people are at 25 tables. It works every time, as long as the equation is correct, which this one we can check. So let's check. I'm going to pick 4 tables. Okay, I'm just plugging in my table number to the equation. And solving it. Following BEDMAS, I get 10 people. And we had 10 people at 4 tables. I could check another one just to be sure. Maybe I'll check 3 tables. So I'm plugging in 3 for my table number. And that should be equal to my people. Again, just following BEDMAS to solve this. Oops. And I get 8 people for 3 tables, which is also true. I could check for all of these examples if I want to, but I can tell you right now, I promise it works. Okay? So now we can use that equation to get how many people are at 6 tables. We already figured that out because we could draw a picture, we could continue the pattern. If I continue the pattern and just add 2 more, I should have 14 people. Okay? So I'm not actually going to plug it into the equation because that one's a little bit easier. For 10 tables, I don't want to go through the pattern, so I will use my equation. Plugging in the number 10 for my number of tables, that should give me the people, and I can say there will be 22 people at 10 tables. The next one, 25, that's a really big one, so that's definitely not one that I really want to draw or follow the pattern with. I get 50 plus 2, which gives me 52 people sitting at 25 tables. So there's lots of different strategies we can use to continue patterns and find the relationships between two different variables, in this case, tables and people. One of the strategies we use, drawing. Another one we use, following a pattern. And the third one, the most consistent one for any type of variable number, right? If it's a high number or a low number, it still works, is the equation. Okay? All right, now we have another example, sort of similar to the tables and the people, but in this particular example, we're now dealing with plots of a garden, and then these little boards that go around it, kind of like a fence. Okay? So we have a picture up here. One plot gives us 1, 2, 3, 4 boards that go around it. When we have two plots, we have 1, 2, 3, 4, 5, 6, 7, because there's one in the middle, that go around it, and so on and so on. So we can continue that kind of pattern over and over and over again, those kind of pictures. So just like our last example when we had tables and people, we can draw a picture or have some sort of a diagram to represent this information and represent the relationship between the two different variables. In this case, plots and boards. In the last example, tables and people. Okay? So I have up here, use a diagram. That's one way to represent the relationship. Another way that we didn't have on the last example to represent a relationship is by using a table of values. So that's what I have here. Table of values specifies the two different variables. Okay? One of them, the plots, we're going to call it P, just because it makes the most sense. And the other one, the boards, which we'll call B. When there's one plot, there's 4 boards. When there's 2 plots, there's 7 boards, 3 plots, 10 boards, 4 plots, 13 boards. So that's showing the relationship between the plots and the boards. Another way that we can do it, which we did use in the last example, is we can use an equation to showcase the relationship between the two variables. We don't have the equation up here yet, because I want us to try and figure out what that equation would be. So since we're given a picture, we can use this picture to help us with the equation. When we were doing the tables and people, we looked at what stayed consistent and what changes. So I'm going to do that again with this picture. We have 1 plot, 4 boards, 2 plots. So now we're adding a plot, and it seems to be that we're kind of putting in 3 new boards. Okay? When I have a 3rd plot, it seems again that we're putting in 3 more boards. When I have a 4th plot, we're seeming to put in 3 more boards. Okay? So it looks like consistently the thing that's changing is that we're putting in 3 boards every time there's a new plot. So what I'm going to do is try out an equation, and I'm going to say 3 multiplied by my plots. The reason I'm multiplying is because I'm thinking of it as 3 boards per every new plot, just like we thought of it as 2 new people per every new table. Okay? So 3 new boards multiplying by the plots, and I'm going to see if that's equal to the amount of boards that I have. Okay? So in the first one, if I have 1 plot, and I multiply that by 3, then that equals, or that should equal, if my equation is right, the amount of boards. 3, unfortunately, is not the amount of boards that I have around it. I have 4 boards. Okay, so something is wrong here. If I look at the next one, and I plug in the 2 for my plots, that should be equal to my boards if my equation is right. 3 times 2 is 6. But I have 7 boards here. So both times I was just short 1. So I think I'm going to change my equation just a little bit and see if that will help me out. And I'm going to add 1 to it. Okay? And now I'm going to try it on the 3rd example. So if I take 3 times the number of plots, which is 3, and add 1, hopefully that will give me my boards. Following the order of operations, I end up with 10 equal to my boards. And if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it works out. Okay? Now I'll just make sure with the 4th example, see if this will work again. It should, if it is the correct equation. Multiply those guys, add one more, and hopefully there will be 13 boards. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So my equation works. So what I did is I tried to find what was changing consistently and then use that in my equation, but I had to just make a small adjustment. Okay? So that is a good equation to represent. However, if you weren't given a picture and you were given a table of values instead, you can still use this relationship to build your equation. So what I'm going to look at here is trying to get from the plots to the boards again. Okay, so I need to get from 1 to 4. Well, first thing I want to do, or at least the first thing I think of, is if I want to get to 1 to 4, I'm just going to add 3. So I'm going to take my plots and add 3. That should give me boards. So I'll try that on the next example. If I want to get from 2 to 7, and I add 3, 2 plus 3 is not 7. So that equation is not going to work. Yes, I know we already know the equation, but just bear with me. Let's pretend we don't. In the next attempt that I'm going to make, I'll go back to this. If I want to get from 1 to 4, I can multiply by 4. So I could go 1 times 4 will give me the boards, or the plots times 4 will give me the boards. So then I'll try that on my next one. 2 times 4 gives me 8, not 7. So once again, this doesn't work. So now I have to figure out a way to get from one to the other with a consistent relationship. Okay? When I added the second example, I was too low. When I multiplied, I was too high. So now I'm going to try multiplying again, but I'm going to go less. So instead of multiplying by 4, I'm going to multiply by 3. Okay? That should get me to boards if my equation is right. Well, 1 times 3 is just 3. In order to get to 4, I would have to add 1. Okay, let's try the next one. 2 times 3 is 6. In order to get to boards, I add 1. 3 times 3 is 9, plus 1 is 10. 4 times 4 is 12, plus 1 is 13. So you can use the table of values to get yourself the relationship as an equation as well. I know we already knew it, but now you can do both versions. Now that we've learned how to get an equation from a table of values, we're going to do quite a few more examples of that. So over here, I have my first table of values. We've got D and S, and then we've got all of our numbers plugged in. So I'm trying to get from the D to the S. First one, from 4 to 10, my first option is just to add. I can try adding. So to get from 4 to 10, I just need to add 6. I'll write that down as my equation. And I look at the next one, from 5 to 11, I can just add 6. From 6 to 12, I can just add 6. From 7 to 13, I can add 6. So this works, and I don't really have to do anything else. There's my equation already. So that's really nice. If I look at the next one, from 7 to 119, if I try adding right off the bat, I would add 112. From 8 to 136, if I add 112 to 8, I don't get 136. So adding is not going to work. The next thing is to try multiplying. Well, off the top of my head, I don't know if I can multiply 7 by anything to get to 119. Maybe I could check on a calculator. But I actually have another plan. Something interesting that we didn't really talk about on the last table of values. So let me show you. This side of the table of values is just going up by 1 every time. On the other side, I have a consistent pattern as well. It's going up by 17 every time. Okay, so I add 17 each time to get the next value from side to side. So I'm actually going to see if I can use these numbers to my advantage somehow. So I'm going to focus on the 17 because we know that adding anything from one side won't get us to the other side. We know that we need to multiply maybe, so we can try that. If I multiply any of these numbers by 1, well, I'm not going to get a number as big as 119 for 7. So I'm going to try multiplying by 17. Okay, so I'll take 17, multiply it by d, and then see if that equals p. If I typed it in my calculator, which I don't have with me right now, 7 times 17 is 119. If I go to the next one, 8 times 17 is 136. If I go to the next one, 9 times 17 is 153, right? You can do this obviously in your head as well, or just like by writing it down on paper rather than using a calculator. This is just multiplication. You guys know how to do this. It might take a little bit longer. You don't need a calculator. It's just maybe a little bit faster. Anyways, multiplying by 17 works. And the last one is the most obvious. 10 times 17 is definitely 170. So that works. So we managed to use this pattern. So if I go to the next one, the left side is going up by 1 every time. The right side is now going up by 14 every time. Okay? So I'm going to see if I can use the same trick. I looked at what my right side was going up by, went up by 17, and multiplied by that, got me my answer. Okay? This side going up by 14 every time, so I'm going to take this b variable, multiply it by 14, see if it gets me to n. Okay? If I take 7 and I multiply it by 14, unfortunately, I don't get 109. I get 98. So that doesn't work. Okay? How do I get from 98 to 109? Well, I could try just adding 11. Okay? If I look at the next example, taking 8, multiplying it by 14 will give me 112. And if I add 11 to that, I get 123. So that one works with the pattern as well. I can try it with 9. If I multiply 9 by 14, I get 126. If I add 11 to that, I get 137. So this pattern is working. I was able to use the 14 as a number to multiply with. I had to do a little bit more work by putting in that 11 with it, but I still got to use that trick. So if I go to the next one, in this one I'm going up by 1 every time on the left-hand side. On the other side, I'm going up by 20 every time. So I'm going to take 20 and multiply it with my g. Okay? If I multiply 7 by 20, I get 140. 140 is not equal to 125, but if I subtract 15 off, then it is. So this is a 5, and that is an S. Okay? I can try the next one. 8 times 20 is 160. Minus 15 is 140. 9 times 20 is 180. Minus 15, 165. 10 times 20, 200. Minus 15, 185. This pattern keeps working. So we kind of found a way, a little trick, to help us with our equations, get them a little bit faster. If I go to my next one, going up by 1 every time on this side. On the other side, oh, looks like I'm going up by 20 every time again. So I'll use that 20 to multiply, multiplying it by my W. And when I multiply 4 by 20, I get 80. So I just need to add 8 more. And that gets me my Y. 5 times 20 is 100, plus 8 more. 6 times 20 is 120, plus 8 more. 7 times 20 is 140, plus 8 more. So that one works as well. Now we'll go to our last one. On the left-hand side, oh, we're actually going up by 2 this time. So I'll write that down. And on the right-hand side, I'm going up by 12 every time. Okay, so now I'll use that. I'm going to take the 12, multiply it by my first variable, my x, okay, and see what happens. So 4 times 12 would be 48. If I want to get down to 26, then I would have to subtract 22. hopefully that's equal to y. If I try the next one, 12 times 6 would be equal to 72. If I subtract 22 from 72, then I get 50. So it's not working, okay? But you might notice there's something wrong, well not wrong, but there's something different about this example compared to all the other ones, is that my left side isn't going up by 1. So this trick might not help us anymore. What I'm going to do to fix that, so that I can still find a way to get this equation, is I'm just going to figure out what my middle values would be. So I have 4. Let's figure out, following the pattern, what would happen if I had an x value of 5. Okay, so we know that 12 is between these two, 2 is between these two. Okay, so if I want to go from 4 to 5, now I'm just going up by 1 instead of 2. So when I go on this side, on the right-hand side, instead of going up by 12, I'll only go up by 6, right? The reason why I'm choosing 6 is because originally I was going up by 2 on the left-hand side. Now I'm just going to go up by 1, so I'm cutting that in half. On the right-hand side, originally I was going up by 12 every time. I'm going to cut that in half and just go up by 6. So the corresponding value, 26 plus 6, is equal to 32. Okay, 32 plus 6 is equal to 38, so that's good. 38 plus 6 would be equal to 44. So that would be for an x value of 7. 50 plus 6 would be equal to 56, so that would be a value of 9. So now, even though my original table of values didn't have them going up by 1, I've kind of manipulated so it is. If you're like, where the heck did you get all those values, Ms. Wallace? I was just following the pattern, so watch what happens. 4, 5, 6, 7, 8, 9, 10. We're going up by 1 every time on the left-hand side. Okay, obviously not from 4 to 6, but from 4 to 5. And then on the right-hand side, originally I was going up by 12, so I cut that in half. Now I'm going up by 6 every time. So 26 plus 6, 32 plus 6, 38 plus 6, 44 plus 6, 50 plus 6, 56 plus 6, and so on. So I still have a consistent pattern, still have a consistent table of values. I've just introduced some new values so that I can still get the left side going up by 1. Now, the right side is going up by 6, so I'll use 6 in my equation. 6 times x, okay? So 6 times 4 would get me to 24. If I add 2 more of that, gets me to my y value. Let's try it with another one. I'll use one from my original table. So 6 times 6 is 36, plus 2 more is 38. 8 times 6 is 58, 48, not 58, plus 2 more is 50. 10 times 6 is 60, plus 2 more is 62. So now my equation works. So when I found a table of values that wasn't going up by 1 on the left-hand side, I just manipulated it. I found some new values that still work with the pattern so that I can still use that trick to find my equation. Now you don't have to do it that way. Remember back to our example when we had the plots and the boards, we found our equation without using that trick, right? So you don't have to use it. I just find it kind of convenient, right? If you have a left-hand side that's going up by 1, you might as well use that process because it's just a little bit quicker most of the time. We have just one example left. I know it's been a long video, but hang with me. We're learning so much. We've got an airplane. It's cruising at 10,000 meters. Then it starts to descend to land. So it's dropping down a little bit. We're told that we have a table of values that describes how much time is going by and then how the height is changing as time passes, as it starts to descend or as it continues to descend. We're told that it's happening at a constant rate. So what I've already done is I've looked at my table of values. I've noticed that the left side's going up by 1. Perfect. And the right side is actually going down by 300. So I put a negative 300, right? It's going down, so I want to make sure I include that negative instead of all of our other examples which were positive. And my first job is to write an expression for the height in terms of time, okay? So I don't know that we've talked about expressions a ton so far this year. It's very similar to an equation, but we just don't need an equal sign. So we're told that this expression should be for height in terms of time. So we want something to do with time would be equal to the height if it was a full equation, but we don't need the full equation part. Okay, so what I'm going to start by doing is just kind of starting what our equation normally would be from this table of values. So I know that my right side is going down by 300 every time, right? And I'm going to multiply that by my left-hand side variable, which is a t for time. In order to get from the left-hand side to the right-hand side, if I multiply 0 by negative 300, well, that's just going to give me 0. So I better add 10 whole thousand to that in order to get the height. I can try that with the next example or next part of my table of values. Negative 300 multiplied by 1 is negative 300. If I add 10,000 to that, I would get 9,700. Okay, so this equation is working just like we found before. Notice that I just used the word equation. The way that I was using it was as an equation, but the way that I have it written right now is an expression. There's no equal sign. I'm relating these numbers together. We're using time, okay, because it asks us to be in terms of time, and this is representing the height. So we're describing the height with that expression. So that's really all the difference between the expression and the equation, is I just don't need the equal sign. The next thing we're asked to do is write the equation that relates time and height. So we've basically already done that. We have that negative 300 multiplied by time. We need to add 10,000 to that, and that will be equal to the height. So the only thing that changed between these two is now in my equation, I have my equal sign. Part C, we want to know the height of the plane after 15 minutes. Okay? So I'm going to calculate that using my equation. Taking that negative 300, I'm going to put my 15 minutes in for time. Maybe double check in questions like these to make sure your units work out. They tell us 15 minutes, and my table of values was in minutes, which means that my equation is as well. So I'm good. I can just plug in 15 for t, add 10,000. That should be equal to my height, so now I just have to solve. Negative 300 multiplied by 15 is going to give me negative 4,500. And I need to add 10,000 to that to get me my height. When I add those two up, I get 5,500 equal to my height. But because this is a word problem, right, where we're talking about different variables that have units, we should probably put the units. The units for height are in meters, so it would be 5,500 meters. Normally I would want you to even write a sentence, but I'm lazy right now. Okay, last one. How long after beginning its descent does the plane land? So this one's interesting, because they didn't tell us a number anywhere. They didn't tell us after 15 minutes or after it descended 3,000 meters. It doesn't tell us anything like that. It just says how long is it going to take for the plane to land. Okay? So we're looking for time in this scenario. We don't know what that is. So in my equation, that's the t. I don't know what the t is, but I would want to solve for it, which means that I need to know the height in order to solve for it, right? We only ever solve equations with one variable at a time, okay? So, here's my question. If the plane is landed, how high is it off the ground? Well, it's not off the ground. So it's 0 meters, okay, at that point. That's what you have to gather from this question, is that when your plane is flying through the air at 10,000 meters, and then it starts to descend, and then boom, it lands, it's no longer got a height off the ground, it's literally just at 0, right? So that's the key with this question. all of this will be equal to the height, which is just 0. So now I can rearrange this and solve. I'm going to add 300t to the other side so that I can separate my variable and my constants. And the last thing, divide by 300 on both sides to get my final answer for the time. So 10,000 divided by 300 will give me 33.3. Repeating, I need units. We're talking about minutes. So I just need to say it took 33.3. I'm just going to round it. I won't have to keep the repeating because it doesn't specify in the question. Minutes. That's how long it took the plane to land. Thank you for listening to this long video. Just a heads up, something I didn't talk about yet. When you build your equation from your table of values, use the variables given to you. So they tell us to use t, they tell us to use h. That's why I use t and h. Don't stray from that. Don't pick your own. Okay? Give or use whatever you are given. Please and thank you. Okay, bye-bye.